I would like to welcome all of you on behalf of Work Package 6, Task 1 of the GÉANT project. And we have a very tight program. Please all stick to the 15 minutes that were attributed to your topic. If there are questions from the audience, if there is time within the 15 minute slots, feel free to ask directly. But you can also type questions into the chat, and I would ask the speakers to then maybe go to the chat after the presentation and answer the questions that were presented there. So it's 1 o'clock sharp, so please let me welcome Lee Johnson from Toshiba. Lee, the floor is yours.
Thank you, Susanne. Let me share my screen here.
It looks great.
Okay, wonderful. And let me get the laser pointer going here as well. Here we go. Okay, thanks everybody and good afternoon. I'd like to talk about the technology we have at Toshiba, the value we bring, and touch on some of our deployments. So Toshiba has had a strategic investment in the quantum technology area for over 20 years now. I work for the Quantum Technology Division based here in the UK, and we provide a range of research and development, commercialization, sales and support of a number of different quantum technologies, including single photon sources, quantum random number generators, QKD, twin field QKD, satellite QKD, KMSs, general cryptography, integrated quantum, photonic devices, and quantum repeaters. And our vision for quantum really is in the next 5 years, we foresee a global platform for a quantum secured network. So this is a secured comms platform for the quantum age and immune from future computing threats. And in 10 years, or maybe a little longer, we predict pervasive use of this quantum secured network, leading ultimately to the deployment of the quantum internet, which will link quantum processors and have advanced quantum IT security tasks, etc. From a QKD technology perspective, we've had over 20 years in R&D and commercialization of QKD. We have a number of firsts. We were the first company to show QKD over 100 kilometers, first company to show QKD over 1 megabit, then over 10 megabits. We've done a lot of work in looking at different types of access networks, and we've done a lot of work in ensuring that multiplexing can work very well with our system. We were the first to show twin field QKD, which promises to extend the reach of terrestrial QKD to 600 kilometers or more. We are developing QKD on a chipset. And all of this 20 years or so of R&D has resulted in the launch of our commercial product around about 2 years ago. During this time, we've had a number of validations. We deployed our first QKD network in Vienna in 2008, and we've deployed other networks globally, Tokyo, the UK. We took part in the Open QKD program. I'll touch on that later. And more recently, we've deployed a quantum secure industrial deployment and also a quantum secured metro network commercial trial with BT in the UK. So our two main QKD products are our long distance product and our multiplex product. The long distance system works in the C band. And, you know, we're quite prudent when it comes to our technology. We specify the system performance in terms of bit rate at 300 kilobits, but we typically see more than this, you know, at 10 dB loss. We have a high optical loss budget. Again, we specify to 30 dB in both our products, but the products will operate beyond this. So some of the key features that we have with our technology are high secure key rates, long range, high optical loss budget, the ability to work very well and coexist with QKD and data services on the same fiber. We have auto setup and alignment and active stabilization features in the QKD system. We have integrated key delivery network system and a KMS. And we were heavily involved in standardization of the ETSI interface and other forthcoming ETSI standards. So we have a KMS system as well, and we abstract the key delivery layer from a physical layer. So this allows us to have a logical key delivery overlay, whereby we can route keys to any QKD appliance connected to the network. And there are other features that we have, such as key rerouting and capacity-based routing algorithms, etc. So looking at some of the deployments, this was one of the open QKD deployments that we had, and it really shows the high bit rates that we can achieve. So here we use QKD to protect data in transit between medical centers and data centers. And also with a partner, we use Shamir secret sharing to protect the data at rest. It was a very successful deployment. And as you can see, we had some quite high secure key rates. Also, we'll be doing work with a number of operators. This is public knowledge, this information I'm showing here. So we've done some work with researchers at Orange, and they showed that the Toshiba commercial QKD product has the ability to coexist very well with conventional DWDM data services. So it was co-propagation of QKD at 1310 nanometer and 1550 DWDM services. They showed 60 channels coexisting at the same time with the QKD information, but also high optical launch power, around about 70 dBm. Alongside this, they had secret key rates over a range of fiber lengths. And they also proposed a co-propagation efficiency, a new metric by which somebody could potentially evaluate the multiplexing performance of a QKD system. And this is based on the fiber length, the key rate, and the optical launch power. So as I said, this is public, and you can download and have a look at the paper at the following link. We've done some work recently, which included our active stabilization. So if you're in a harsh environment with potentially vibrations from rail or road, or maybe even overhead fibers, and then potentially disturbances in the fiber due to temperature, we mitigate against this by using our active stabilization. So we provide dedicated pulses embedded into the transmission signal. And these provide a reference for some self-correction algorithms that really reduces the system noise. And it means that we can deliver the best performance in challenging and changing circumstances. So recently we had a deployment in the Czech Republic. It was a 46-kilometer fiber link between two stations. And it was a busy route. You know, every 5 or 10 minutes, there would be customer or rail traffic, 5 meters from the rail line itself. We deployed our multiplex system at 1310 nanometers, and the folks provided a dashboard using SNMP-v3. And what it showed was, after some baseline testing in the lab and the actual trackside fiber deployment, the stabilization worked very well and provided high rate, low noise, long-term operation. So we have a number of deployments globally. In the US, we did some work with JP Morgan, and we showed how QKD can be used to protect blockchain applications. We have ongoing evaluations by Verizon. We're doing some work with the Chicago Quantum Exchange and an energy operator in the States. We have some work in the UK, and I'll go into more detail on that. We took part in Open QKD over the years. As I mentioned, Orange France have done some evaluation of our technology. Over in Japan, we're doing some work with NTT on QKD and PQC, working together. And we've done some long distance hybrid QKD network demonstrations with KT. So I mentioned the work we were involved in with Open QKD. We were involved in a number of test beds over the years. So we were securing medical data in Cambridge. We did the rail infrastructure work in the Czech Republic. In Madrid, we were involved in a use case for securing end-to-end communications over 5G networks. In Berlin, for securing 5G communications backhaul. In Poland, we did some work in connecting some data centers together to keep information confidential. And in Vienna, we did the work with the information in transit and at rest with the public healthcare system. So one deployment we have is in the UK. This is an industrial deployment of a quantum secure network. So this is the Center for Manufacturing and the National Composite Center. So over here on the right, this is a compute center, and it really controls the machines at the National Composite Center. So over standard BT fiber, we protected the traffic between the two sites. And the requirements were quite stringent. They wanted to use high bandwidth and encrypted communications between the sites. Everything had to be fully commercial and off the shelf. They needed simple installation and sort of hands-free ongoing operation. And also it needed to exist with a current network and manufacturing workflow. More recently, we've announced in conjunction with BT, the UK Quantum Secured Metro Network. So this is in April 22. This is the world's first commercial trial of a quantum secured metro network. It's operated by BT, excuse me. And it uses the Toshiba QKD and KMS systems. So it's a core ring around an area of London, and we use fibers for the access tails. And really, this is providing high bandwidth data services using QKD to protect this. The area of London where it is a high value target area. So there are lots of media, data centers, and other enterprise customers that will be able to use this. And the QSMN itself will explore potential future offerings, such as encrypted links and also quantum keys as a service. What's different about it is it's deployed in an operational environment, a real network, not a laboratory. It is a network itself, not just a collection of point-to-point links in a chain. All equipment is telecom approved and commercial off the shelf. It uses BT core fibers and BT OpenReach standard access fibers. QKD and data exists in both the core and the access links. And we use the key management system to deliver keys to any connected node. And finally, it's all integrated into BT's network management operation. So the value we bring with our technology really is in the high optical loss budgets that we have, up to and over 30 dBs, which gives you flexibility in your design, but reduces your CapEx and your OpEx. We have high key rates, which can help with the number of users and use cases and help you with an element of future-proofing. Our system works very well and easily integrates into today's networks. And we've shown this with the deployments we have and also the multiplexing work we've done. You know, we're a large company, so we have global deployments, diverse use cases. We have something like 46 companies across Europe to help scale and build QKD networks. And we have extensive and continued R&D leadership. So we are a global leader in R&D research, and we're actively researching and commercializing new types of technologies such as twin field, QKD on a chip, satellite and beyond. And we have a European focus. So combining the technology with our support capabilities and our R&D capabilities, we feel strongly that it helps ensure success for today's and tomorrow's QCR deployments. Thank you.
So thank you very much. We have time for questions. Are there any questions?
Yes, I would.
Please go ahead, Peter.
Just yeah, a short question. Toshiba is not a EU-based company. So do you have problems, let's say, to go into the security environment of EU countries?
No.
No. Okay.
No.
Thanks.
No problem.
Any other question?
Oh, I forgot, by the way, if you'd like any more information, check out our website or send me an email.
You had some interesting use cases. I was happy to see those in the presentation. And I think I see somebody raised their hand. Manfred Nihus, please go ahead for another question.
Good morning. Just one question regarding the twin field method. No? To what extent will this trade off key rates and the overall and distance, and to what extent will this be something which will be relevant for longer distances? If you can comment on this.
Sure. So we're still developing the twin field capability, but in terms of distance, so we showed in a laboratory we can go to 500-600 kilometers and still maintain healthy key rates.
Okay, thank you very much.
We have time for one more question. I don't see a question, so thank you very much, Lee Johnson, for presenting the Toshiba solutions. If there is any other question that we didn't get to now, please type it in the chat. And so thank you again for this excellent presentation.
Thank you.
So let's now move on to the next slot, which is LuxQuanta. We have Vanessa Diaz, the CEO, who will present
Hello, everybody. Do you want me to push the slides or do you have
Yes,
them
please
here?
go ahead and share the screen, then you can control
Okay.
it as you like. You have 15 minutes and you can either fill it with the presentation or leave room for questions and answers.
Okay. So I'm supposed to be sharing my screen now. Let me know when you can see it. So
Yes, we can see it perfectly.
All right. Well, hello, everybody. It's really an honor being here with this community, telling you about the foundation of our company and the version of the quantum key distribution technology that we work with and we're commercializing right now. So I'm Vanessa Diaz. I'm the CEO of LuxQuanta, a background in telecommunications engineering that moved into the dark side, as I call it. No, I'm more in the operational and commercial side of the business right now. So what we brought is a flavor of the technology that, as of today, very much complements what we've seen from the discrete variable QKD manufacturers. We are born out of a research center placed or located here in Barcelona called ICFO. It's very renowned in the research environment for working with photonic sciences. Whenever they craft technology that is very disruptive and is aligned with what's demanded out in the market, they build a company. And that's how we were born back in May 2021. So we are barely 2 years old. The technology that we inherited from them, though, it was already quite mature because it's the result of 4 years of incubation. So since we were born and we inherited that technology, we've been working very hard to release the first system that I'll show you in a minute. We are already 22 team members, very highly skilled team. It's very important for the work that we have ahead. So we are highly qualified, I'll say, on the technical side, particularly. We have, of course, our parents, no, is the same institute that we came from, ICFO, public research center, same as ICREA. But we also secure private funding from 2 very important companies. One is very well known in the telecommunication industry, is Corning. That's where I came from, actually. I was there working for over 11 years. And the other one is GTD. They work with software for mission critical systems. They put this in space. So we inherited a new flavor of quantum key distribution called continuous variable. I'll explain to you in a minute if you're not familiarized with it, the benefits that it delivers and how it complements and can be extremely competitive, no, in metropolitan areas that we are targeting. So what we see in the industry consolidated now for quite a few years is discrete variable. Is a version of the technology that codes the information in, let's say, a property of a photon. In the receiver, this conditions very much the machine that they have, not to read this information. They have a single photon detector. This is great to allow for long distances, as you are familiarized with. It's not very great in terms of co-propagation, so that's why we hear often that they have to move things around in the wavelength spectrum of the optical fiber, just to make sure that it's quite enough for this single photon detector to work well and deliver a key rate that is continuous and reliable. What we do is code the information instead of the property of a photon is very weak pulses of light. So it's more like the type of approach we use in the telecommunication industry. We have a carrier and we are coding the information in the amplitude and the phase. This allows us to have in the receiver, contrary to that single photon detector, we have a coherent detector. So we have a local oscillator in the receiver that is just tuning into that specific wavelength where the information is being sent. This is great because it allows us to deliver or enable very high co-propagation capabilities. No? So what this means is that in the C band, we can actually tune the quantum channel and it can coexist with any other distribution of data, wavelength division multiplexing, so DWDM or CWDM and any other schemes that we need, like for example in the access, no, frame relay or Ethernet. The other thing is though that right now the distances that we cover are around the 40 kilometers. So this means that we are beautifully equipped to operate in metropolitan areas where those distances are notably reduced compared to long-haul links, and where in fact the capillarity of the amount of links that we have is higher. So we are very disruptive. This technology it was born to stay and actually make a name in the industry on itself, because it can definitely deliver, because of this co-propagation capability, lower total cost of ownership. So in terms of capex, no need of any dark fiber, no need of pushing the information around in the same optical fiber. And also it has the potential to deliver a completely seamless integration because, and this is the second value that it adds, the components are very mature, off the shelf from the telecommunication industry. This delivers great performances. So for example, when we think of a central office where temperatures can go well beyond the maximum range of operations that we see in the old version of this technology, because the components are very mature, we can cope with those kind of environments more real, no, let's say. And then scalability is important because we are meant to rewrite the way that quantum key distribution is being employed out there. We want to make this system very scalable, benefiting from photonic integration. So all the optical components are now going into a chip in the transmitter and the receiver, an optical chip, and that's going to allow us to be very competitive and allow for this technology to be mass deployed. That's the objective that we have in mind. So just so you understand the value of what we've done so far with the release of our first system, I thought it was good just for everybody to review the layers, no, that our systems are made of. So we have an optical layer. That's where these optical components live right now. As I said, we buy them off the shelf, so you can buy them in any website, in fact. And those components are the ones that, controlled by a very strong firmware, are crafting that quantum signal that is pumped into the optical fiber. There is a next level, has to do with all the signal processing, because at the end you have to assemble these quantum signals. They are difficult to craft, and once you've pumped them into the optical fiber and receive them on the other side of the link, you have to extract them and separate them from the inherent noise of the channel, no? And also you have to be able to separate what is the channel noise and what is an intruder. So that's how the technology works. So this level is pretty critical, and we have implementing algorithm there that is allowing us to deliver a very high performance, no, compared to what's been out there in the literature. Last but not least, the software layer is actually the bottleneck for continuous variable QKD. So these two layers that we are looking at right now, so signal processing and the software layer, that's where the know-how goes. It's a lot more complex, these two layers, compared to the old version of quantum key distribution, or discrete variable. And this is again where there's a lot of know-how. So the team in LuxQuanta, they have crafted a software that allows to adjust to the characteristics of the channel. So you can actually unplug it from one link, plug it into another one, and you'll be able to tell what's the best set of parameters, not to deliver the best signal to noise ratio, and therefore the best key rate. So the system was officially commercially released in February this year. We became the first manufacturer of continuous variable QKD to release this commercial version of this technology. So since it's been a little bit haunting, actually, the level of attention that we've been getting from around the world, because there is a handful manufacturers in the entire world. We are European, truly, so our shareholders, the majority of them are European, and also we have European control. So this means that anything that is installed from LuxQuanta today at the governmental environment or public kind of networks, that'll be granted to be there later on when the requirements are more stringent, no, from the European Commission, and they ask for a European manufacturer. So we tick the box in that particular characteristic that for the community that I'm talking to today is, I believe, super important. So the system is called Nova LQ. Is this first version. While we work on that photonic integrated version, it's already delivering or ticking some of the boxes from this vision that we have on continuous variable QKD. It's already easier to deploy. Again, it's tunable on the C-band, the quantum channel, so you don't have to move or shuffle things around. You just have to plug the system and off it goes, because it's been automatized very much everything, no, that has to do with the setting up. So delivers very high coexistence capabilities with, as I introduced before, coarse wavelength division multiplexing or dense wavelength division multiplexing alongside other type of wavelength schemes that you need, no, particularly in the access, as we were discussing before. And then it's already adjusting to the characteristics of the channel again, because this know-how that has been implemented over the last 2 years in particular. And it's already equipped with the HC interfaces that allows the system to speak to any other machines in the ecosystem. At the end, you have these pieces of hardware in both sides of the link continuously creating keys and then sending them, no, to the encryptors, and also working with multiplexers as well, so you can combine all the information in one optical fiber. So it's already been designed to operate with HC4 and HC14, both of them. So right now the distances are around 40 kilometers. The key rate is on a few dozens of kilobits per second. We can share with you the system specifications after this call. Depending, of course, on the signal to noise ratio that you have in the channel, that key rate is going to oscillate. It's the same as for everybody else, but it's already very competitive, no? Looking at the level of refreshment that you need of the key, considering applications that are going to feed from these systems. So the technology has been tested. Actually, there are many more collaborations at technical level, as well as proof of concepts with many entities across the world. We cannot talk about them just yet, but they'll be popping up soon, starting after summer. So the first test that we did was with the local government of the region where we were born, Catalonia, and it was a point-to-point connection between the governmental office building and the research center where we were born from. It got a lot of attraction. It was covered by the press, and the president of the local government actually came to present, no, at the event. It was a video conference secured with our technology, with Nova LQ, and it works beautifully well. It was 30 kilometers distance, as I introduced before, point-to-point link. And since we've done other tests, so the technology is ready to be tested. So we envision this year as cornerstone, no, crucial for us to let you know about the technology, the capabilities, understand as well yours, and then move forward now to an even stronger commercialization phase. So in January this year, we also secured important funding from the European Commission. You know very well about this project, EuroQCI, very ambitious and with a lot of funding as well from the European Commission. You know as well, if you want to qualify to get this type of funding, you have to be European. So again, tick the box on that, and we assembled what we believe is one of the strongest consortiums of all the ones that won this fund. It's a 10.8 size kind of project for over the next 2.5 years. We're going to mature the systems with our partners to make sure that it's ready for this very ambitious deployment of this EuroQCI project. So we're going to match the requirements in terms of maturity, industrialization, as well as standardization. That's a work that all the manufacturers on QKD, we are working very hard on. We know it's very important. So we are the core of this call. So the biggest chunk of this fund is coming to LuxQuanta, in fact. But again, we are very thankful to the partners we're working with, from the component level to all the way up the very customers themselves with Telefonica, no, at the very top of it. We're working with them. Actually, our system is in their network right now, and it's been working solidly for months now and delivering great performance. So that's it. This is I wanted to just introduce you the company so you know who we are, where we're based. You put a face to LuxQuanta, and also you understand the capabilities of our technology, what it's capable of doing. We will be very much keen to sit down with you and explore whatever project that you have and show you, the fantastic co-propagation capabilities and reliability that this flavor of quantum key distribution, continuous variable, can deliver for you. So thank you very much.
Thank you very much. Very interesting. We do have time for a few questions. Does anybody have a question?
Maybe I have one question. Do you already have a finalized product that you can sell right now? If not, when do you plan to have one?
No, we have one. Nova LQ is ready for proof of concepts. So we just have to get in touch and let us know when you think that you might need it, so we can plan accordingly the delivery.
Okay, thank you. Any other question? We still have a bit of time. You should quite a big laboratory. Is that also in Barcelona?
We do, yes. We have a 100 square meters lab and another high-tech lab of 30 square meters too here in Barcelona. That's where all our R&D and our production is right now located.
Okay. Are you also working
sorry.
on interoperability tests with? Oh, I see there's another question also from.
Hi, Suzanne. And I'd just like to ask the question, is there plans for larger DB budgets than 8 dB is quite limited to the access? Are there plans to do longer distances?
Oh, yes, the work continues. I think I can speak for in general, the industry. So I think in general, no, quantum key distribution manufacturers, we are always working towards pushing this maximum reach of our systems. That's one of our strongest R&D lines. So you will be seeing us challenging that maximum distance over the next few months. Yes, definitely, yes. This technology actually has a lot to offer. This is just the beginning of a really exciting R&D development.
Thank you.
Okay, so thank you very much. I'm afraid we are at the end of this segment. Let's thank you again, and let's move to QTI. Is Alessandra Matais on the call?
Hello, everybody. I'm Tommaso Chipinti. I will speak about QTI.
Okay, great. Please go ahead.
Okay, good. Give me 1 second. I share the screen. Okay, do you see my screen?
We see the desktop. Now we see the full screen.
Okay, perfect, perfect.
Please
so
go
thank
ahead.
you very much. Thank you very much, everybody, the organizer and who will listen to my talk. I am Tommaso Chipinti. I am one of the founders and the CEO of QTI. We are an innovative startup. We are quite young in the sense that we incorporated in 2020, and we are a spin-off of the National Research Council, the Italian National Institute of Optics in Italy. We have our headquarters, you see here in Tuscany, in particular in Florence, but we have also a second office in Rome, where we essentially follow more the commercial and business development topics. As you see here, we have some important, let's say, stories to tell you, but probably the more important is that we, in 2021, to receive an important investment by a telecom operator in Italy, TIM, in particular made by Telsi, which is the company in charge of all the cybersecurity topics of Cypher and cybersecurity topics of the TIM group. They at the beginning of the story in 2021, they bought 33% of the company. Then after 1 year in 2022, they bought again other shares, and now they are at 49% in our shareholding of the company. We are at today 30 persons, increasing, because we are improving a lot the production facilities and the quality management system part of the company. Just to, as a presentation, showing you one of our first results, which is quite important in the sense that we build up the first international 3-nation QKD system, in the sense that in 2021, during a G20 in Trieste, we made this network connecting Trieste to Rijeka and to Ljubljana through a trusted node in Postumia. This was quite an interesting example of technology, quantum technology, but also logistics. Think about just speaking 3 different operators, telecom operators. Think about all the possible problems that can arise just to build up a temporary system that was made essentially in some days and then stayed up for essentially 1 week over there. So it was a great result at the time. So as you probably understand, we think that these 3 logos represent us in a very peculiar way, in the sense that we think that we are very strong in the European and international market of QKD, because we do the QKD technology, I mean QTI. Telsi has the ciphering units, so hardware, professional hardware, top-level ciphering units, and TIM has all the capabilities for interconnection and backbones to access network in Italy and also in Europe to another company. We are member of this kind of organizations, International Optical and Quantum Organization. We are very proud about that. But I think that it's important to share with you this slide, showing you that we won a first Horizon Europe project concerning photonic integrated circuit for QKD. So we are working on a PIC just to shrink down the dimension and increase the performance of our system. I mean, it's a low tier level project, this one, Prometheus. The other two are essentially, I'm sorry, QSUB is a national research project funded by the defense, in particular from the Navy. And we are performing QKD underwater in free space channel. So we want that defense project. The other two, ECHO and QUID, are EuroQCI projects that we won together with other fantastic partners. We can say that we won an industry one and a national deployment one. The industry is led by TIM, so our shareholding company. The other one, the other project is, let's say, the head of the QUID project is in the hands of INRIM in Italy. Then also we made and we won a project on OpenQKD program. That was interesting because we applied the QKD in the so-called Industry 4.0 application. So we were making essentially an absolute security between a Industry 4.0 machine with cloud capabilities assured by edge servers that were in the TIM network, and we were assuring with quantum security that particular link. We are, as a company, operating in all the three environments, let's say. Of course, our main focus is on ground, in the sense that having Telecom Italia, we are pushing a lot the fiber optical in any kind, let's say, fiber optical application, both with dedicated fibers, but also, and in particular, with WDM traffic, so the fibers with traffic. And we operate also underwater with fibers and also in free space, as I already told you. This is our project, our product. This is a product. The name is QuellX. Here in the picture, you see both Alice and Bob, because it was essentially a demo that we were performing in the same room. But I will give you more detail just in a few seconds. QuellX is a product, but also is a family of products, in the sense that we can approach different network topologies and also different lambda, different, let's say, quantum channel configuration, spanning from C-band to O-band. So it is very flexible, and we can adapt to the needs of the customer. The family is divided into three. We have the QuellX, which is the generator of quantum key of quantum keys. The QuellX-C is a combination of the generator of the keys together with an hardware ciphering units, which is an L3 encryptor. And then there's the QuellXR, which is essentially a version of QLX more related to research activities. And in that case, I mean, when I say research activity, I mean more academic research, not industry research. And in that case, we give the possibility to the researcher to take the raw data coming from the instruments and perform, for example, their own algorithm to perform all the other tasks of the QKD. I mean, this is just an example. We have a second product that is called QKME, which is our key management entity. It's a 1 unit 15 inches rack system that is capable of managing the keys generated by the QLX system, by the key generator. It is compatible with the two standards, the ETSI ones and the Cisco SCIP. I mean, maybe many of you knows that Cisco has his own management system for managing the keys around their equipment. We already are compatible with them, and we are working with Cisco to implement real installation around their customers. Just to show you some additional details regarding, on the left side, you see, for example, more details on QLX. For example, we provide 2 kilobits per second of secret key rate at 14 dB of losses, but we can, I mean, by standard, I mean, when you ask a premium connectivity, premium capability, we can reach up to 20 dB, but speaking with some compromises together with the customer, we can reach additional and more demanding losses in the link together with the customer. Of course, we also we are compatible with superconductive detectors, which enables us to reach very long distances in the connections. On the right side here, I just reported some characteristic of the products of the ciphering units that we attach together with our key systems. This is one product made by Telsey, but just and it is good in my opinion because it's a level 3 ciphering unit, so it essentially creates a VPN that is hardware ciphered, and it uses the quantum keys in part, I mean, to encrypt essentially, and also to authenticate the systems. It can operate also in a mesh network, of course. This is another slide just showing that we can work in WDM. And for example, just to show you an example, on the right side, you see one of the latest products by Cisco, which is a physical layer encryptor that can go much, I mean, around 200, 400 gigabits per second, but also in some particular cases can reach also the terabit of ciphered, physically ciphered traffic. And it is essentially a WDM system. So we already implemented all the software and physical tests with them, and the system is working.
You have 1 minute left.
Yeah, I finish. Just to show you that we implement also an SDN agent into our equipments. It's an optional. We think it's very important to be compatible with the ETSI 15 standards and the new ones that are coming. So we insert the agent inside the KME essentially, And we can provide also a specialized SDN controller for the network. This is something that we discuss generally with the customer, if they really need this, or if they prefer to work straight with the single links in their networks. Just to show you my last slide, we are very proud to say that some days ago we performed a very interesting demonstration hosted by the European Commission and the Swedish presidency. We perform a very interesting demo, speaking together different brands. And just to show you that from a QKD point of view, we were compatible between QTI and LuxQuanta, just to give you this information. And there were also other partners, for example, the Polytechnical School, and also Rode Schwarz, and also Telsi, giving all the layers of this very, very important interoperability demonstration, all based on EU 27 vendors to the European Commission. And this is my last slide. Thank you.
Thank you very much. And very interesting, your interoperability setup that you had.
Yeah, it was interesting, yeah.
So unfortunately, time is up and we don't have time for questions. But if anybody has a question, please post them in the chat, because we now have to move on to the next slot. Thank you again for the presentation.
Bye.
Bye-bye. And let's now move to Ulrich Eismann from KEEQuant.
Yes, thanks for having me over here. I hope you can understand me well. I'm sitting here on a trade show in London, so the audio may be a little bit compromised. And
no
I
problem,
apologize
no
in
problem.
advance.
We'll manage.
Yeah, yeah. Also, I couldn't see Tommaso's slide beforehand, so I hope everything works well with my screen sharing. So let's give it a try. All right, so let's share that. No, it doesn't want to share.
It doesn't want to share what you get a
yeah, it says screen sharing, but it doesn't give me the share button.
Can you send us the slides in the chat and that we can try to share it? Or maybe we can move it into the next presenter while we try to sort this offline, and then that you can take over after.
That would be awesome if you could do that.
Okay, so the next one would be Cisco. We have AJ Pandey and Amjad Inamdar.
Hi everyone. Good morning, good afternoon, good evening. So let me share my screen and let me know if you can see it.
We can see it, but it's not the presentation mode. But if you want to keep it, it looks like it might be, yeah, now it's perfect.
Okay. So hi everyone, let me introduce myself. My name is Ajay. I am a product manager at Cisco within the enterprise routing group based out of Bangalore, India. I have with me Amjad, who is a principal engineer in the same group. And we will today walk you through quantum safe encryption for IKE v2 IPsec using RFC 8784 and Cisco SCIP. So I'm sure the audience here is very well aware of all the challenges to traditional encryption with the advent of quantum computing. So I will not go into that just for the sake of time. But the main concern that we have today is the bad actors can store the data today and decrypt later, right? We know that there are various options being discussed right now, such as PQC algorithms, QKD and everything. But having said that, those who want to really break into data, they can very well do it today, right? So what's the solution which can fit into today's environment, right? We know that PQC algorithms are getting evolved, but are they mature enough to be integrated in existing products? Probably not, right? When they will be, we are not very sure. So what's the solution from Cisco side, which can help integrate today's network and make them quantum safe, right? That's where we are introducing quantum safe encryption based on RFC 8784. So this is based on importing a post-quantum pre-shared key. During this session, I would also be using the term PPK, which stands for post-quantum pre-shared key. So this key can be either imported from an external key provider, or it can be configured manually also. So we'll go into details of that in upcoming slides. And this solution that we have today is available generally. We have documented on the Cisco configuration guides, so it is available. Now with that, let me go into the details. So when we talk about normal IKE V2 key derivation, which is based on Diffie-Hellman or ECDH, that takes in the shared secret, puts it through the key derivation function, and we get the session key, which is not quantum safe, right? That's a challenge that we have. Now, how RFC 8784 plans to fix that is by putting another key into the mix, and that's the key what we call as PPK, which is mixed with existing Diffie-Hellman shared secret, and the final session key that you get is quantum safe. This is the basic premise of RFC 8784, that if we use pre-shared keys, then along with the existing Diffie-Hellman and ECDH, the resultant that we'll get is going to be quantum safe, right? What the RFC does not tell us is how these keys will be transported from one end to another end, right? From the initiator to the responder, right? So that is where we will talk about solution from the Cisco side, which takes in RFC 8784 and augments it and makes it really ready for adoption, right? So this is one of the methods which with which you can use it today. This is what we call as manual PPK. You have two routers, initiator and responder, and you configure the RFC 8784 using whatever configurations we have, and you also configure the optional PPK, right? So once you configure the PPK, it's on the admin to make sure that on both the ends, same PPK is configured. This PPK, along with the ECDH or Diffie-Hellman shared secret, results in a quantum safe resistant session key, right? So that is one way of doing it. It's very quick. If you have routers today already in your network, you can very well do it, and you can be basically quantum safe, right? So this is one of the solution. And now this is another solution, right? So this is what we call as dynamic PPK, right? Quantum safe encryption with dynamic PPK. Here, the key is something you can import from an external key source. So it can be a QKD device, it can be a cloud-based key provider, anything which can implement the SKIP protocol. Now, the next logical question might be, what exactly is SKIP protocol? SKIP stands for Secure Key Integration Protocol. This is what Cisco has developed for its encrypted devices to talk to external key provider. It is based on HTTPS, and the channel between the router and the key provider is again secured based on TLS 1.2 and pre-shared keys. So we are not using standard encryption there. We are using pre-shared keys. So that's where even that channel is quantum safe, right? So SKIP is HTTPS based. The initiator or responder will talk to the key provider, fetch the key ID, and the key providers will in turn talk out of band and synchronize the keys among themselves, right? So if we talk about QKD vendors, they have their own channel, the optical channel, to transport these keys from one end to another, which is quantum safe. Then there are other key providers outside QKD who use PQC algorithms or whatever proprietary methods they have to provide quantum resistance on that outer band channel, right? So that's something guaranteed by the key providers. From the Cisco side, the routers talk to the key provider using the skip APIs on HTTPS, fetch the key and the key ID. The key ID is in turn transported to the other end to the responder, and then again the responder uses that key ID and talks to its corresponding key source and gets the actual key, right? That's how it really works. Once you get the key ID on both ends, both the devices can mix that key ID with the session key and get the final quantum resistant session key. So that's how it really works. The beauty of this is already available, documented, and I've put some Cisco documentation links here. Actually, we have done a lot of proof of concept and integration with many leading QKD and key provider vendors, both from the traditional QKD world as well as the key providers who are using cloud as the key delivery mechanisms. So we have done both types of integrations for federal customers, for finance customers, all across the globe, right? So this is pretty well tested, and now it's also available for general consumption also, right? This is today on iOS. So these devices that I'm showing here are especially for IQ2 IPsec. They are running Cisco iOS XE operating system. So typical enterprise routers, like I think in previous sessions somebody was showing Catalyst 8000 routers. So those do support it. On another class of Cisco products from the service provider space, this script works with the MACsec, and today here what we are showing you right now is very specific to IQ2 IPsec, but we have implementation for MACsec also. Similarly, on Cisco side, I think the previous solution, the manual PPK, has been implemented for the ASA firewall. So overall within Cisco, we have this solution implemented across the portfolio, and at the same time, we are also looking into future strategy, how we can evolve, make a complete story, including the PQC also. So that's an ongoing effort that we have at Cisco side. Yeah, that's pretty much what I wanted to cover. If there are any questions, I'm happy to take them. Or if Amjad from our side wants to add something, and please go on. I believe we have maybe 4 or 5 minutes more.
Yes, thank you very much. We do have ample room for questions.
Okay.
I see Mario, please go ahead.
Yes. Okay. If I understand correctly, you have a PPK system which works with the pre-shared keys, which you can expand, if I understand correctly, by quantum safe functions. So if this is correct, why do you need QKD at all? And why do we need it?
Yeah, so I think the question here is, from where do you get PPK, right? So one way of getting the PPK is by manually configuring on the router, right? But that's again an overhead, and again on which transport you will configure it. If you are using SSH, which is again prone to, you know, whatever threat we have on traditional cryptography, same is applicable on the SSH transport also. So maybe one crude way would be you log in through console connection, configure the manual PPK on both ends, make sure it is same, and then yes, it will work, right? There is no need of QKD in that scenario. But again, it's a lot of admin overhead. It's good to test it out. Maybe if particular organization has a way to make sure that the PPKs are easily configured across the devices, right? Then yes, there is no need of QKD. But in another scenario where we want a more automated way of key transport, right? And I think there are customers who basically don't trust SSH and these things for even configuring basic PPK, right? So in those cases, you'll have the reliable QKD based transport, which is proven to be quantum safe, right? Because they are using the optical channel. So based on customer requirements, we have both the flavors. If they want to manually configure a PPK or a password or to whatever you call it at each end, that is there for them to test out. But if they want a more robust quantum safe channel based on physics principle, then yes, that is also there, right? So Amjad, do you want to add anything?
Yeah, just to add in this diagram, PPK source can be a QKD device. So if we have a pair of routers, initiator and responder, each connected to a co-located key source, typically co-located at the same site, and that PPK source can be a QKD device, which provides synchronized keys on both the sides. So the key material that the QKD provides is treated as a post-quantum pre-shared key, and that is used by the router and used to derive the IK-IPsec session keys. So the other use case of that is we use the key that we import from external key source like QKD to derive the session keys for MACsec in another class of routers. So essentially the PPK source here is can be QKD device, or it can be cloud-based key providers, which use PQC or other techniques to transport the key in an interception-proof manner on both the sides. I hope that answers the question.
Okay, thank you very much. If there are any other questions, please post them in the chat. And I would like to thank both of you for the presentation.
Okay, thank you so much and have a good day.
Thank you, you too. Ulrich from KEEQuant, do we have the green light? Or do you need more time for testing with Ivana in the background? And we should move to the next slot in the meantime?
I didn't get your slides. I've sent you an email and also some messages in the chat.
I saw the slides, but okay,
so
then probably we will mention the background.
Okay, so good luck. Let's move then to the next vendor, which is Nokia, and we have Yannick presenting. Please go ahead, Yannick.
Okay, can you hear me?
Yes, very well.
Okay, good afternoon. It is an honor to have been invited to speak in this Infoshare session. My name is Yannick Gauthier. I'm a product line manager in Nokia.
Sorry, we don't see the slides yet.
Really?
Yes.
So I was saying
now it
that,
looks good.
Okay.
Now it looks very good. Thank you.
So my name is Yannick Gauthier. I'm a product line manager in Nokia for optical security and enterprise in the Nokia optical division. I will briefly introduce you our quantum safe network solution that we in Nokia had initiated many years ago already. Security is we believe security is one of the most important issues that the telecom industry is facing today, and our company is committed more and more to achieve high security standards. So the security goals are guiding the way we run our operation. We train our employees and to ensure that we are aware of the security roles and responsibilities. So it's all about, let's say, also the many security policies, practices, which need to be aligned with international standards and best practices. And what we understood is that the regulatory requirements are increasing, and the pressure, the liability of our customer, of the service provider, of the mission critical providers are also increasing. So we are working with customer, with partner, with supplier and government agency and also third parties to improve the overall security model. And that's true for let's say for the supplier, for the system we are using for our product. We have a design for security methodology framework, a huge framework, and We have also dedicated dedicated services and a department for security intelligence and automation with smart solutions for that. But obviously, what I'm going to speak about is about trusted connectivity. So let's say we are selling across the different layers encrypted connectivities, and that will be obviously it's the way, let's say, how strong is going to be this encryption and how much it could resist to the quantum risk is definitively what we're going to cover now. Some security breaches are growing at an alarming rate of I don't know, maybe 1,500 records stolen every second, at least in 2021. And enterprise and network operators are telling us that it's urgent. They need to secure business critical information. The regulatory pressure is increasing also. So they need to strengthen their security to minimize the risk of loss of breach of sensitive data. And that are distributed well beyond the organization boundaries, obviously. So and firewalls and other mechanisms like that are definitely not sufficient. So the need for new technology, and especially for in-flight data, for data traversing the network. So cryptography algorithms are definitively considered strong, but not because they are mathematically, impossible to break, but because they are computationally prohibitive. So our understanding, our view is that it's really important to match the key strengths with the encryption algorithm strengths. So I think it's a well-known paradigm that the overall solution will only be as strong as the weaker of the two. So just like the locks in the house are only as good as the weakest one. So as quantum computers continue to advance, they will pose a significant threat to cybersecurity, and this computer can perform or will be more and more able to perform calculation much faster than the classical computer, and cyber criminal will be able to break public key-based encryption algorithm, for instance, and perform cyber attacks are let's say not possible today. So the quantum safe encryption, but also the quantum safe key management is a fundamental piece of our offering and our overall defense in depth strategy that protects business critical data. So it's we believe that they're on the market. We believe that top security standard requiring 256-bit strands should use an IS 256 algorithm with 256-bit key size, and this solution is quantum safe and secure from compromise from many practical quantum computer attacks in the foreseeable future, at least. And the product, I'm not going to tell much about our product here. Our product is our portfolio is for key management is the pillar for that is Nokia 1830 SMS product, which delivers quantum safe centralized key management for the overall cryptographic lifecycle of each IS 256 encrypted wavelength services, for instance. But it could be also for not just optical services. It applies for different layers, and it interpret with the network, the transport layer, the transport network, and so that the connectivity could get quantum safe key and enable this quantum safe encryption. The model, the framework we have put in place is that as per defense in depth paradigm, encryption, cryptography could apply on different layers. And so as we started on the layer 1 optical layer 1 encryption with OT&SEC, which has its own value proposition with a low cost per encrypted bit, extremely low latency and bandwidth efficiency. It's multi-services, it scales easily and support many traffic type. It has high bandwidth and robust network protection but the same approach is also being extended for some other layer where encryption is extremely meaningful and depending on the traffic type, on the use case and network architecture. It could be at layer 2, at layer 3, and we have extremely strong solution in catalog to build this type of encryption, quantum safe encryption at the transport network layer. This connectivity, I mean, these are typically, let's say, long-run connectivity and not ephemeral connectivity, which are the one we are having, let's say, as usual typically, and where asymmetric encryption typically applied today. And this asymmetric encryption is typically the one the one is extremely vulnerable to quantum risk. Instead, our view is that our technology, which is a pre-shared key symmetrical encryption, IS 256-bit, is quantum safe, but still we want to, and that's what we are doing, we want to develop new models, new mode, and new framework, so that the key won't be just provided as it is sometime on some network as a pre-shared key delivered by the officer, but it could be also, let's say, the centralized key distribution, which is a typical mode of operation that we most of our customers are having with the 1830 SMS, where the regulation and the security agency are perceiving that as a single point of trust. And on top of that, we have made add so that we could integrate now with let's say some infrastructure, with quantum QKD infrastructure, so that the key could be, first, we could still have orchestration as a key, and the key policy and the key rotation as we are having today on our network, and the customer are using that, but now doing that with key which are going to be generated from the QKD infrastructure. And at the same time, because we are having also research on PQC with our, let's say, Bell Labs, Nokia Bell Labs colleagues, working not just on the physical part of the game, but also on the mathematical part with PQC. We are also working on extending the solution with PQC, as anticipating a bit what is being, let's say, under standardization definition by the NIST. And we are doing that not just in optical network, with our let's say our optical portfolio, but also for submarine, also for IP, MPLS, and microwave infrastructure. So what we did is that we define different blueprints, and one blueprint. So for a long time already, I told that we have been delivering quantum safe layer 1 encrypted connectivity, and many enterprise and operators have deployed it already. So we need to take that into consideration, and what we wanted is definitively to enable that journey for everyone. So we have a blueprint where the classic blueprint is definitively the one where the key are centrally managed, and the entire the full life cycle is being managed by a crypto officer. And And in this mode of operation, which is quite common into the network, the key and their associated policy are generated centrally and even stored centrally. The key are distributed, and then after suitable authentication and authorization to the application or to the endpoint on request, where the key are ephemeral actually. But already in 2017, we Nokia collaborate with the customer.
You have 1 minute left.
Yeah, in APAC, and we did let's say let's say in a model where we have this integration with the QKD, and that's what we are leveraging now, developing a multi-vendor integrated solution that combines the benefit of 1830 quantum safe solution with more QKD technologies, and we are even working on to make that broader and to a low integration with a satellite QKD. So it's important to say that we have been pleased to collaborate with the University of Athens and GÉANT, who is a major provider in Greece, and coordinate the LuxQCI project in this POC, which are several steps, and we did one recently publicly in Vienna, and another one, a new step is in preparation, where we made that integration of connectivity at 500 gig encrypted connectivity, where with products which are today working worldwide, we were able to implement, let's say, to implement that integration of using using a multi-link QKD infrastructure, and more is coming now. Last is just to tell you that definitively, I think our customer are telling us that the time is now, because you need their need for preparation to evolve the infrastructure, and you are the one who are specialists of innovation with your customers, the research institute, the university. So we want to support you in that journey. We have solutions which are ready today, and you could add this quantum enablement or quantum readiness as you want, and actually we are doing that every day, and we made even yesterday an announcement in that direction with an important provider in Europe. Okay.
Thank you very much for your presentation. Unfortunately, there's no time for questions, but if you do have a question for Yannick and Nokia, then please put it in the chat. So thank you again for presenting. I hear we have the green light on KEEQuant. So please share the slides and
okay, I'm sharing my screen now. Can you please stop sharing your screen?
Yeah.
3 is a charm, that's what they say, right?
Exactly.
Excellent. So thanks for sharing the slides. Maybe we can directly go to slide number 2. It shows a very bold company motto: we secure European infrastructure. And for KEEQuant especially, that means that we work in the domain of cybersecurity. I'm on the cybersecurity structure right now, and a big plus for any cybersecurity company, of course, is to have, in the case of EU27, to have only EU27 money in the company. So maybe next slide, please. We founded the company in 2020, so that seems to be quite a universal date for building QKD startups in Europe. I told you already, 100% EU27 shareholders, so any euro that went into the company is purely EU27. The company is based in Fürth, which is close to Nuremberg in Germany. We have 8 public funded projects at this time, and I will tell you a little bit more about this later. We are 17 employees, and of course, just like all the other companies, that number is continuously rising. We also based the company on the novel scalable CV QKD technology, so technology with continuous variables, as we could hear from LuxQuanta before. And based on this, we have two product lines available. One is the QKD itself, and the second is a key management layer. So next slide, please. Just to give you an idea about the scientific background we have at KEEQuant, this is the Max Planck Institute in Erlangen, which is very close to the company located. There has been a lot of pioneering work on CV QKD for a long time, and of course a lot of predecessor projects, which then eventually led to funding KEEQuant. Next slide, please. And along these lines, you get to go into contact with quite a few people. I don't want to mention them all. I just want to mention that we co-founded the German Industry Club for Quantum Security, DIFQSEC, which you find in the right-hand upper corner, together with players like Deutsche Telekom, OHB, Rohde and Schwarz Cybersecurity, ADFA, and so on. So I don't want to name them all. Next slide, please. And next. Unfortunately, I cannot introduce all the people to you, just for lack of time. I just want to give you an overview about the 8 projects which we have ongoing right now. So on the key management side, we try to arrange the projects a little bit according to the product lines here. On the key management side, you find DemoQuant. That's a QKD link which is currently being installed between Berlin and Bonn. The lead of the project is Deutsche Telekom, and of course it will use and employ their fibers. There are quite a few hops in between, and the main aspects of this project are basically all the compatibility and operability of QKD in such a network. So there are a lot of aspects covered also on the KMS side. On the right-hand side, on the QKD side, you can see the secret project. This is part of EuroQCI, so it's one of the EuroQCI industrial projects. It's actually the largest one, and we teamed up with Rohde and Schwarz Cybersecurity to establish, well, the biggest goal of this project, which is to get towards a QKD system which is certifiable. We didn't say it's certified simply because of the lack of time. Again, it's just 3 years, so it's hard to actually go to certification. But the target is to definitely have a certifiable system with all the information written down it takes to go to certification. Another part of this project is also to miniaturize the QKD and to bring the continuous variables on an optical chip, and I will say a few words later. Also on the QKD side, we have quite a few German projects. Quincida focuses on putting QKD into the free space realm. So basically, you see telescope, you would replace the fiber between the Alice and Bob by 2 telescopes. Decode is about a photonically integrated receiver, and the ProQuake is also a QNet follow-up project where the idea is to have post-processing algorithms inside of a database which people can then access to do their QKD research or product development. And the fourth project, Rohde and Schwarz, and it's also part of the QNet follow-up project system. We're also part of the German Squad project, so that's more like a politics-sided project. The idea being to coordinate the national efforts in Germany and not have people invent the wheel a second time all the time. And on the space side, together with OHB, we are developing what may turn out to be a space-proof quantum random number generator. Okay, next slide, please. And then next slide. And again, next slide, please. I'm sorry, it's easier if I present myself. And again. So that's the nicest marketing slide I think we have, and it gives a little bit of a perspective of where we are heading with KEEQuant. So the idea of the company is not only, but also to produce a kind of Me Too products, the products which also our competitors are capable of producing, at least from the user side. So it's basically 19 inches rack system, which has a few height units, which is pretty costly and also costs quite a lot of electricity and space to operate, and of course a lot of money. But the idea is to actually shrink down QKD to a format which is scalable first of all, but which is also much more producible and much more easy to roll out in, let's say, greater market segments. Not only in people who can afford like the big boxes on the left-hand side, but who actually need something which is small and invisible essentially. So with the continuous variables QKD, which we use, you have the ability to actually put the entire functionality, so including the detectors, on a single chip, on a single photonically integrated chip, and have all the electro-optical functionality running there. And that's not something which we just come up with, but it's rather a standard technology which you find in the coherent telecom sector. So if you think about these standard pluggable modules like CFP or SFP standard formats, that's the way we are heading. And along this direction, we have recently achieved quite nice results. So we have our first chips, we have them running in the labs, we have fibers connected to them, there's light emitted, there's light detected. So a lot of the basic functionality is already there, and we will then along these projects which we have, we will develop the technology in a way that it's actually going towards product. So next slide, please. Next slide, please. Next slide, please. Next slide, please. And again, next slide. So just to give you a quick overview about the QKD system and where we stand right now. Again, that's kind of the first generation QKD system, which has a 19 inches format and which comes, of course, at a decent price as you're used to in the market already. Next slide, please. The name is Endarial, and in this slide we wanted to give you like a few of the specs which we have in the system. So it's based on coherent modulation. It's CVQKD. It's operated in the C-band, so you have a tunable laser inside. You can tune it to any of the WDM channels which you have in this band from 1530 to 1560. At this point, we still require 2 dedicated dark optical fibers, but of course this is subject to change in the future. The idea, of course, being to reduce the necessities to just a single WDM channel. All the key delivery interface, all the contact to the outer world, so to speak, to the key management system is of course based on ETSI 14. So that's kind of the industry standard right now. And the management is done by a browser-based GUI, but many customers also ask for command line interfaces, so there will be something available, and also a REST API maybe inside. Next slide, please. So of course everybody asks us for the specs, and that's also, let's say, a commercial trade-off right now. The target specs which we have in mind, but that of course needs to be confirmed, is 10 kilobits per second at 10 dB loss with an asymptotic security proof and a reach of 16, so 16 decibels. But again, that is subject to change probably in the future. Next slide, please. Of course, if you want to go from, let's say, from a single QKD link to a network, you need a key management system, and we have a solution on that side as well. Next slide, please. We actually built some dedicated hardware. This was kind of one of the first projects of KEEQuant. This is something you can, we have already installed at the customer side and operated, and people are really happy with it. It's standard 19-inch rack appliance. with all the necessary high-speed connectors which you need to operate it. Next slide, please. You get a nice GUI, so that's if you want to set up like an early testing network or something like this, where you need a lot of flexibility and good operability, then probably this is something for you. Everything is again compatible with ETSI 14. You have the REST RP endpoints with gigabit performance if you buy our hardware. And of course, you also have the vertical vendor independence, i.e. you can connect any QKD system or any encryptor to it, given that they are compatible with ETSI 14. And with this, I want to say thank you and leave 1 minute for questions.
Perfect timing. Thank you very much. Yes, 1 minute for questions we have. I do have a question. That the chip that you showed, is there any timeline yet when this will be coming out?
As a product, it's a bit hard. I mean, we definitely aim for the second part of the decade, let's say. Anything else would be much too early. But again, shrinking down things and having things operating in our lab already promises us that we will be there as soon as possible.
Yeah, and we're looking forward to this. So thank you very much again. And thank you for doing this in these challenging environment and background that you have.
All right.
We
Thanks
have
for having
now
me.
a break until 14:45, and then we will continue with 5 more interesting presentations. So I'll see you in 15 minutes. The next slot would be IDQ. Is anyone here from IDQ? I don't see Simon Patkovich. If that's not the case, then I would say let's skip this for now and let's go on to the next vendor, which is Ribbon and Ronan Cohen. Would you like to go ahead, please, Ronan?
Yes, let me share my screen.
Perfect. Looks perfectly fine. Please go ahead.
Great. So yeah, basically, Ribbon is providing networking equipment for optical infrastructure and services. And we have done providing encryptor, layer 1 encryptor for many years. This is our successor, TM400 ENB, which provides muxing of services in any rate. The encryption here is done selectively per service. We're doing the highest level of encryption with AES-156 with standard elliptic curve or Diffie-Hellman. We're integrating post-quantum cryptography and quantum key distribution in our portfolio. And this card is FIPS compliant against physical tampering. Actually, this card is currently under testing in a certification lab. This card can be installed in any Apollo 96 series chassis, giving the best of size and cost effectiveness in every place in the network. So basically, the standard encryption is done via, of course, 2 encryptor each and every side. And in our portfolio, the services are going into the WDM or OTN network and providing safe services from peer-to-peer and also from networking perspective all over the network, again, per service according to customer needs. And this is a very good revenue generating machine engine for our customer, of course, service provider. And of course, end customers can also have a control over their service encrypted service, whether it will be encrypted or not, determine several parameters of the encryption, and so on. So basically, yeah, so with the standard encryption, we have authentication of each peer towards the other peer. Of course, we are using certification and private and public key. And then we, after that, going into symmetrical encryption with AES 256 with GCM. And the Muse SDN controller that controls the Apollo network enables control of the key rotation and additional parameters of the encryption that the user, I mean the service provider, or its end user, of course, can control over those features. So what happened when we're introducing the QKD into the blade, the TM400 ENB? Basically, we are receiving the key from the QKD devices over QKD 014, the ETSI interface. So on one side, the encryptor, the Apollo encryptor, not generating his own keys, but receiving the quantum keys from the collocated QKD devices, using those keys, encrypted the data, transmitted over the DWDM network over a long distance fibers. Again, we are taking the QKD devices quantum channel requirements as defined or as customer requires, whether it will be a dedicated fiber for the quantum channel or integrated into the filters over the network, and this a bit decrease the distance. And the sync channel basically can be equipped into the filter itself. So again, whether it will be dedicated quantum channel or into the DWDM filter, then it depends, of course, on the application and implementation. Regarding the integrated control, so of course, here are several options. We have the API from the KMS towards the Muse controller, and then we'll have a very simplified GUI cut-through for alarms and events. And we can also implement, depend of course on the application and the needs, the advanced ETSI standard for SDN controller orchestration. So let's
You're breaking up. Maybe turn off the video so that we can get better sound.
Options. Susanne, can you hear me? Am I audible?
I can hear you now. I can hear you. That
Okay.
you were gone for a second. So
Okay.
please go ahead.
Okay, great. So authentication of the peers, of course, is the same way, using certification with certification authority. And we also need to certificate from the QKD device towards the Apollo nodes, again with certifications. So once we have established those peers and the peer from the QKD towards the collocated Apollo, then we're able to do the authentication and receive the primary key from the primary QKD node towards the primary Apollo, and we can then encrypt and decrypt the service. When the key rotation reached, then of course, the Apollo encryptor requests a new key from the QKD primary, and it's provided, and of course, the key ID is sent over to the next peer, and the secondary Apollo encryptor receive the symmetrical key, and by that, of course, we can encrypt the service with QKD keys. Regarding the PQC, so we are, of course, following the NIST process. We can use two algorithms for the KEM and for the SIG. For now, we are adding the PQC in addition to the Diffie-Hellman. And once, of course, again, when the standard is finalized, and we can not just adding the PQC in addition to the Diffie-Hellman, but of course use the PQC algorithms in order to give quantum safe algorithms in the encryption itself. Again, it depends on the application. Some customers will wish to adopt QKD, some others will adopt the PQC, and again, the Apollo encryptor is supporting both. Regarding the management, the Muse controller control each and every parameter in not only in the optical networking, but also in the layer 1 encryption. So it's about what mode we wish to operate the card, defining, of course, the GSM mode, the Diffie-Hellman group, the frequency of the key rotation. If the customer wish to add a pre-shared secret, then he can do it in the Muse controller. And regarding multi-tenancy means management of end customers. So Apollo support multi-tenancy. It means that a customer can have a slice all over the network. He can have a slice of the optical network. He can have a slice by the port and the service, of course. And when a customer wish also control the encryption parameters, that he get this tenancy and have full control, of course, over the encryption services. As by that, this control is moving from the service provider to the end customer. So my last slide. So again, we are leading with 400 gigabit per second encryption uplinks. The services can be selective. It means that one service in the blade can be non-encryption, and the other one can be with encryption. The Muse domain controller is managing the whole network, including, of course, the encryption part. And regarding quantum safe, so we are adopting the PQC algos. We have interop with multiple QKD device vendors, well established and also startup. All is based on the ETSI 014. And we are performing some customer trials in order to present the capabilities, as mentioned, not only with one or two, but all the vendors that supports the standard ETSI. Yeah, that's it. Time for questions.
Okay, thank you very much. Yes, indeed, we do have time for questions. I saw you mention once that it was for C-band. Is it for C-band only? In one of the slides?
Well, basically, ribbon support C and also C+L. Again, it's very dependent of the implementation in the network, the tolerance, the fiber not only the fiber capacity, but also, the fiber health. So we can, of course, start with the C-band, and when the network is exhausted, we can expand it to the L-band. So yeah, we have a variety of solutions, depends, of course, of the needs and the application.
Okay, thank you. Any other question? The Apollo box that you mentioned, is it, do all the boxes come with the Muse controller and the QKD plus PQC, or is it something that you would standard customize basically, or is it one box that automatically has all the three components in it?
We have for the depends on the application and the capacity and location of the site. We have few variety of Apollo 96 boxes, and this blade is suitable for each and every box. And of course, standard encryption, PQC, and QKD are supported within the blade, and by that, support in any Apollo chassis.
Oh, okay.
And of course, you can accumulate multiple encryptor, whether it will be standard or QKD. For instance, one blade can operate with a standard. In the same chassis, one blade can operate with a QKD, another one with PQC.
Okay, thank you very much. Any
Thank you.
other question? This does not seem to be the case. If another question does come up, please put it in the chat. But thank you again, Ronan, for this interesting presentation. Let's now move on to QBird. Ingrid Roman is on the call, I believe.
Yes, I am. Thank you. Can you hear me?
Yes, perfectly fine.
Perfect.
As soon as Ronan stops sharing, you can. Okay, thank you, Ronan.
Okay.
Please go ahead and.
Yes. Let me share my screen. Put it in presentation mode.
No, no, not yet. We see the thumbnail slide. Now it is perfect. Thank you.
Yes, so it's visible, okay?
Yes, it's just like it's supposed to be.
Okay, perfect. So thank you so much for inviting me and giving the possibility for presenting QBird and our QKD technology. My name is Ingrid Romein. I'm one of the co-founders of QBird. And QBird is a spin-off out of QTech, the institute from the Technical University in Delft. We were founded in 2021, so last year, a bit more over a year ago. But we were originally a group inside the TU Delft. So the technology has been under development inside QTech and the TU Delft for over 4 years now. And since last year, our team has already grown to 11 people today. And so far, we're mainly basing our growth on Dutch and European subsidy projects. But we are also already able to provide QKD systems, which I'll explain later. Our long-term goal is to provide hardware and software for future quantum networks, and not just QKD, but quantum networks in general. And let me explain this a little bit because it's a bit different from the other QKD suppliers. So the way we see it, there will be a need for quantum networks on the one hand to connect quantum devices, to scale computing power, distributed quantum computing, and also to connect quantum sensors where similar quantum links are needed. And these same quantum links can also be used to democratize quantum technology, and it will allow users to connect to powerful and expensive quantum computers from a distance with a cheap and simple client device that can still provide a quantum link. But what we're here for today is all about security and quantum security, which we all know is really becoming important in the current geopolitical climate. So protecting governmental communications, critical infrastructures, financial and military data is crucial. And quantum networks and quantum links can provide this. So what we do is we build devices for quantum secure data communications. And the way we do this is we have qubit transmitting end nodes. I don't know if you can see my mouse with the little arrow.
Yes.
Okay, great. So we provide client devices, qubit transmitting end nodes, and they can connect to entanglement generating center hubs. And each two qubit transmitting end nodes or user devices can exchange quantum keys. So this provides the scalability, multi-point to multi-point connectivity, because a center hub can connect more than 2 users. And it also has a higher intrinsic security compared to other QKD systems, which I will explain later. The same center hub, entanglement generating center hubs, can also be upgraded to connect quantum processors in the future. But for now, what we can already do is connect user devices. So just to put this very graphically, until now, QKD systems can provide a user A to B quantum link secured by QKD. What we provide is a center hub that sits in between these 2 user devices and can connect multiple end users that can each exchange quantum keys. So each pair of users can safely exchange quantum keys. So, as I already mentioned, this will provide a multi-point to multi-point connectivity. New users can simply connect by adding an additional end node, and this provides for very cost-effective scaling, because the user devices are very small. They don't require a lot of optics or mechanics. They don't require cooling. They just require a qubit sending device. All the expensive equipment is inside the center hub. This also provides a improved security for the scalability of the concept. Confidential information about the keys is only kept at the user devices. So the center hubs, while they provide the quantum link, they connect the devices, they will never know anything about the quantum keys. So it is, in that sense, an untrusted hub. You don't need to trust it. The key information will never be at the center hubs. It will only be at the 2 users. This technology also gives us the possibility to scale up the distance. We've tested up to 50 dB quantum links, but we can safely go up to 40 or 45 dB loss. This is between end nodes. So this gives us a distance, depending on the quality of the fiber, of course, around 200 kilometers. As I said, this is also future-proof technology. Once you have a network based on this technology, it can be easily upgraded towards a future quantum internet, connecting quantum processors or other quantum systems in the future. And finally, we field tested technology in multiple environments with industrial partners, which is the next slide. So we have deployed the system between various cities in the Netherlands. One of the deployments is shown here between Delft, Rijswijk, and The Hague. We've tested it with industrial players like Cisco, integrated the system with their SCIP protocol, and provided MACsec as well as IPsec encryption. So what we did there is we provided the quantum keys, and the Cisco encryptors, they took up the key. We provided a fresh AES 256 every 30 seconds. This is the key rollover that could easily be managed by the Cisco encryptor. We did a similar test with Juniper. There we used the ETSI 014 protocol, same numbers for key rollovers, AES key every 30 seconds. One of the tests we also did together with Cisco is provide a multiplexing. So with the ROADMs, we could we used to multiplex the different bands. Classical network was going over the C band, and we provided our QKD quantum keys over the O band. So we can work in both the C band, where we are kind of flexible on the wavelength, and we can also provide our keys on the O band. And finally, what we've done with a satellite company in the Netherlands, is a proof of concept on optical SATCOM communication. So what we did is, using the system that has like 2 legs to the center hub, one of these links was a free space link, the other link was provided by an optical fiber, and we were able to provide QKDs in this way as well. And with this hybrid link, so both optical and fiber link, we were able to secure financial transactions together with ABN AMRO, one of the larger banks in the Netherlands. And in fact, this worked so well, this was running for 3 weeks without any interference or any thing that needed to be done on our side. This is a picture of our system as it is right now inside the data centers in Utrecht. It is deployed inside a Eurofiber environment. This is still the prototype system, and we are now working and building up our minimum viable products, or our MVP system, that is available for customers that want to implement it in their networks. And this is an overview of the testbed that we have right now. In fact, it is running. We deployed our setup with 1 central hub and 2 end nodes over a Eurofiber network. This is simple commercial fibers and nothing special about it. It provides key, and we use Uniper equipment to distribute the key and secure the standard data communications. And we've used this testbed to secure some online calls, a couple of digital meetings that we have, as well as some standard digital communication. Another project that we're working on right now, and this is together with the Port of Rotterdam, the largest harbor in Europe, with a couple of other partners. We are building up a multi-user QKD setup to protect information and data communications inside the Port of Rotterdam. And there's many different users inside the Rotterdam harbor that each need to exchange information. So what we'll build up there is indeed such a network that with 1 central hub, we connect 4 or more users that will each be able to exchange the quantum keys. So finally, we're also part of the EuroQCI program. I'm not showing everything that we're doing inside, but one of our main projects inside the EuroQCI project is the MDI Queen project, where we work together with a number of partners on improving and upgrading our system even further, really going towards the next generation QKD device, working with ThinkQuantum on increasing the key detection, with Bright Photonics to work towards photonic integration and towards a quantum chip. And we're working with Secura to go towards certification and well, being able to deploy it and really have this certification of the system at the end of the project. So as a final note, we are, as QBird, building the next generation digital infrastructure. And today we'll build devices for quantum secured data communications. Tomorrow we'll enable general purpose quantum connectivity. We are ready to install our QKD systems inside your networks, and open invitation to join us in the quantum revolution. Thank you. And for more information about our networks or our QKD systems, any technical information, please contact me at ingrid@qbird.nl.
Well, thank you very much. Very interesting use case you have there with the Rotterdam harbor.
Thank you.
I see a question, Peter Kaufman from DFN. Go ahead, Peter.
Hello. Thank you for your talk, Ingrid. I have a question. Maybe I misunderstood something, but as I understood, you have, let's say, 2 hubs which exchange the secure keys, and at each hub you have a number of users, and you said that the keys are only known to the users and not at the hub. Was it? Okay.
So maybe
I did not really understood how that works. Maybe it would, even if you tell something now, even it would be nice if you after our our event provide some more slides or text about that concept. Yeah.
Yes, of course. I can. I don't know if it's possible to exchange email addresses. I can send you a couple of academic papers where our principle is explained. We also have a white paper on the tests we did together with Cisco that I can send your way as well. This goes into more detail on what we are actually doing and the protocols that we're using. So,
okay.
Would that be okay?
Yeah, fine.
Okay.
Okay, thank you very much. I see another question from Mario.
Yes, thank you for presenting the first system that uses quantum entanglement today. Maybe there will be some others, maybe not. My question is, what type of entanglement are you using? Is it polarization or something else?
We are in that sense flexible to the type of qubits that we're using. Our current system is based on time-bend qubits, but we are working with different qubit types.
Okay,
does it answer your question?
Yeah, thanks.
Okay, so any other question? We have room for one more. The field test, did you do also, could you say something about how, if you did any scalability tests, how many multi-points did you maybe try?
So far, the field tests were based on 2 end users, but in the lab, we've gone up to 4 end users. So we're confident that this will also work in the field.
Oh, okay.
And this is what we're going to do inside the Port of Rotterdam. So.
I see. Okay. Okay, so thank you very much. I see Mario still raised his hand. Oh, okay, that's was from before. So thank you again for this presentation, and let's move to IDQ. I hear that all the technical difficulties have been solved now in the background. Simon Patkovic, please go ahead and share your screen. We cannot hear you yet.
Can you hear me now?
Yes.
Oh, fantastic. Yes. So is it 15 minutes, right?
Yes, it's 15 minutes, and you can finish a bit early if you want to give it time for questions, but people can also ask questions in the chat.
Fantastic, thank you. I'm just going to share my slides here, and I'm going to quickly run you through a couple of interesting things. I haven't used Zoom in a while, so bear with me 1 second until I figure out how do you share. And
there's a
green button in the
line,
middle.
yes, in the middle. And you can pick the application.
Let's see if this works.
Looks good. Go ahead.
Looks good. Okay, fantastic. Anyway, so I believe most people have heard of ID Quantique, but if there's anybody new who hasn't heard, just quickly, company started in 2001 with a quantum random generator project based in Geneva, Switzerland. Also now has R&D joint venture in Seoul, Korea, and we have offices in Boston, USA. In 2007, there was the first real-world QKD implementation for Geneva election, and then as we went through the time, there were first, second, third, and now fourth generation of the QKD systems, about 130 to 140 employees. Many PhDs in physics, obviously, and a lot of software developers. So just that would be in a nutshell. We do both quantum safe security products, which include quantum key distribution system and QRNG systems, as well as software that runs to support the key routing for this system, which we call quantum key management software. And as well, we do quantum sensing devices, single photon detectors, and we have manufacturing as well. Also worth mentioning for those who are not aware that There is a company in Vienna for EuroQCI that is independent from ID Quantique. However, since more than 50% of our the components in our product are European anyway, we qualify for made in EU, so we have an independent, or there is an independent company owned and operated within the EU who's able to manufacture and sell made in Austria systems, since the components are majority of them made in Europe anyway. So there's just a quick update for those who've been wondering on that. These are systems from the past. Some of you might have seen them. How things change over generations, as you can see, is just incredible transformation. And we're now down to 1U in the 4th generation, both on COW and QKD protocol. Telecom ready, commercial grade products that are used in production. We're not talking about just research, experimentation and prototyping here and POCs. We're talking on productionized telecom grade products. This is just an example of the most recent products we have. The Cerberus, which uses COW protocol, typically used for metropolitan network due to a shortened distance of the security proof, and Clavis XG, which typically used for backbone network, is based on BB84. So I'm just going to move on just to make sure I'm on time. Why this is all relevant, both for EuroQCI and beyond? Well, because of the, I'm just going to show you a quick timeline. So there's a lot of chatter about post-quantum crypto being released next year. And we work very closely with NIST, BSI, and many other agencies. So we're always in the loop because we also implement some of these protocols in Key Management Suite. But what's interesting is that we see quite a lot of demand and interest from, and these are just examples of different industries that need to implement quantum safe. And for each of these industries, there's going to be a different timeline, from critical infrastructure, cloud providers, PKI, and the network infrastructure, typically 5 to 10 years to upgrade to quantum safe. And sometime in the future, there's going to be quantum panic 5 to 10 years from now, and we're going to have the second wave of adoption looming. There's a lot of, I spent 3 years working on cryptographic migrations and cryptographic agility before joining QKD. And this is a very complex topic that's going to be every help that telecoms can offer to enterprise and government will be welcome. This is why we have focused quite a bit over the past 2 to 3 years to build solutions that can be deployed on a large scale by telecom and fiber optical service operators that can meet these different demands for high SLAs to enterprise and government, because not every enterprise and government customer has the ability to do the both software migration to quantum safe, which is very complex, but also to ensure that there is a hybridized approach with QKD and PQC, which we now see being a trend. And if anybody wonders for recent announcements, you can look up the recent Synctel announcement and recent Nokia announcements on quantum safe networks. So there's more and more interest in hybridizing the backbone of the fiber optical infrastructure. However, the demands are very high for the quality of such complex system. And so we now offer to telecom providers a stacked solution with QKD, quantum KMS, which is very complex. I'm going to show a slide on that. Layer 2 encryptors, but we also work with layer 1, 2, and 3 vendor encryptors, and quantum enhanced KMS, which goes beyond dark fiber. And what telecom operators can provide with this bundled solution is quantum safe bandwidth, for instance, to the downstream customer without customer having to bear any complexity. So key management system is very important enabler of such a solution. So as soon as you go beyond 2 to 3 devices, there are a lot of complexities around how to route the keys, quantum keys in a large network. And so we have developed a very large network in Korea 4 years ago. And over there, we have one QKD complex network with multi-topology. And we have 3 KMS networks running on top, serving three types of customers that do not want to share key routing infrastructure. which are classified level government, non-classified government, and other industrial customers. So interestingly, you have multiple layers. You have the physical optical QKD layer, and you have logical layer, and then you have the encryptor or consumer layer, and they need to have keys with high SLA supplied to them, and they do not care how you do it. It just has to work. So this is one of our areas of expertise, and we see a lot of demand for this around European project, particularly with cross-border connectivity routing. And so just to show you how this looks in Flash, this network, which has both elements of a ring, there are a couple of star elements, and there are a couple of extensions of this network. And so on the left, you have QKD physical layer, then you have the key routing or the KMS service layer, and then on the third, you have the consumer layer where the encryptors are, and there are in between them, they're enabled to have 127 different types of links. And this network spans over 700 kilometers in distance of QKD. So this is one screenshot of how these key management systems have advanced over the years. It looks like any other telecom grade enterprise software. We're easy to manage. There's also a simulator where you can simulate different topologies and how to establish key routing between them. So just to give you a flair that this used to be in the past very experimental, but now it has to be telecom grade with telecom interfaces. This is roughly to give you an idea how the quantum communication layer or QKD layer is able to integrate northbound above itself to encryptors. And these are different types of, not all of them are listed. We have added a couple of ones over the last couple of months, but this is just to give you a flavor that we support all of these critical layer encryptor technologies. And most of these that you see on the slide are in their gold release, meaning they're public on the market. You can simply buy encryptors and consume QKD keys. It's off the shelf. It's not proof of concept. It's actually production software with all of these vendors. And this is very important. So ID Quantique has been very active in helping define standards for interoperability. So what you saw on the encryptor integration is that north arrow going to consumer, ETSI 014. Then you have east-west integration between KMS layers. This is a scenario where you can potentially have one customer being served by multiple telecom operators running multiple KMS systems, and they want to make sure their network can interoperate. So you have to use east-west interfaces with ETSI 014, and then you have to also, in some instances, our KMS has to interoperate with other QKD manufacturers, because obviously telecom, for instance, or enterprise customers do want to have a choice often and do not want to be locked in. So that is another thing in our ecosystem, is that open interface south to other QKD vendors. And then worth mentioning before I close up the session is we also spend a lot of time trying to advance the QKD case on the certification front, which includes also the key management system. And we are as active as we possibly can be on multiple standards bodies, and we are engaged in multiple certification routes, including common criteria, which is now in the stage of defining the protection profile. We're doing a comprehensive security certification and assessment in Korea, which includes both the key management and QKD layer. And we are also very active within all other standards and bodies where there are attempts to come up with a standard approach. As you know, as you all are aware, PQC has been on the forefront, and mostly the agencies such as NIST and BSI and ANSI and others have been putting a lot of effort there, but they are aware they will have to do the same for QKD. So we'll work with them as well to make sure they're up to speed and they can start establishing certification programs for QKD. So Susanne, I think I can stop safely here, hopefully.
Yes, thank you. We do have a few minutes for questions. Thank you very much. The on one of the slides, that use case that you showed with the Korean network, where you have several customers that do not want to exchange keys with each other, was that these customer planes, were they separated by software only or hardware supported?
So so that's a very good question. So because Telecom provided one QKD network, which generates the keys, the customers wanted to have their own ability to manage software that delivers these keys to their own encryptors. So they have their own hardware encryptors, but they also wanted to have their own separate instance of software, which they can control. For instance, they can set their own size of the buffer, because we use buffering to enable supply of keys in case, for instance, an interruption or eavesdropping occurs, and the QKD boxes stop exchanging keys. So each customer can set their own different configurations. And so 3 separate KMS layers run, which would be software-defined layers, on top of one physical optical layer that exchanges keys. I hope that answers it, Susanne.
Oh, yes, it does. Thank you very much. I see one more question. Mario, please go ahead.
Yes, we didn't hear much about the QKD system itself, so let me just ask a short question. Does it work on continuous variables, discrete variables, quantum entanglement, or something else?
So what ID Quantique manufacturers are so-called DV QKD systems. With COW and BB84 protocol. So it's a different system from CV QKD or entangle-based QKD system. So I hope that answers it.
It is single photon based, right?
Yes.
Thanks.
Okay, so thank you very much again. This takes us to the end of this time slot. Thank you. And let's now continue with ThinkQuantum and Marco Avesani.
Hi, everyone. Can you hear me?
Yes, we can hear you fine. Please go ahead. And
you should see my presentation.
Yes, it's perfect.
Perfect. So thank you for the invitation. Marco Avesani, I'm one of the co-founders of ThinkQuantum. And yeah, today, during the presentation, I wish to talk a bit about what this image actually represents. So that is somehow our vision on how the QKD networks actually will be integrated in the classical network infrastructure. So a couple of words about ThinkQuantum. ThinkQuantum is a spin-off of the University of Padova that offers a complete solution for cybersecurity based on quantum technologies. So our products are mainly quantum random number generators and QKD system, both for fiber, free space, and satellite scenarios. We also cover the full value chain. So this means from the design to the manufacturing to the commissioning of the system. And also ThinkQuantum is based in Italy with an Italian shareholder structure, 100%. And so it's a fully European company. And also we are very, let's say we put a lot of attention in our supply chain that it's trying to keep as much as possible as our European supply chain. So we are a young company. We were founded in 2021 from the fusion of expertise, let's say coming from the university research group and the industrial capabilities of our major investor, that is Officina Stellare. But let's say we have a solid background because the university group has more than 20 years of experience in the field of quantum information processing and quantum communication. And on the other side, Officina Stellare is a company that is leader in the design and in the development of telescopes and optomechanical system for observation, laser communication, and defense application, both on ground and on space. So we are also involved in several, thanks to these, let's say, mixed experience, skills, and let's say capabilities that we have. We are involved in several European projects, both let's say Horizon and ESA project. For example, the QSMP flagship project, QDICE, that is about let's say, developing QKD terminals for CubeSat. GAUM that develops, let's say, optical ground station for QKD, and to, let's say, QPilot as a project on integrated photonics, QUID that is the Italian national QCI, and also SAGA that's a project for, let's say, constellation of satellite, QKD satellites. So this is our, let's say, standard products, our offer. We have TICKE, that is our quantum random number generator, and QKey, that is our quantum key distribution platform. Let's say from the point of view of the quantum random number generator, we have a fairly unique solution because our quantum random number generator is a source, implements a source device independent protocol. And this means that we don't need to trust the source of quantum state, that in this case could be completely controlled by an attacker. And this means that we have an increased level of security directly from the protocol itself. And this is also the only semi-device independent QRNG that you can find in the market that somehow combines an increased level of security with high performances in a plug-and-play device. And it comes into, let's say, two flavors: standalone version that you can mount, let's say, on a rack, 1U, and also an OEM version that, for example, we integrate in our QKD system, but you can also integrate in other products. So as I was saying, the framework is the source device dependent. We have an internal entropy generation rate that is about 2 gigabit per second, and a final secure random bit rate. So what you get out from the device, that is after already the extraction that is done in real time in the device, that is 330 megabits per second. You have a RJ45 interface, and you can, let's say, interact with it via socket stream or REST API. And you can, for example, use it for classical quantum or post-quantum cryptography or simulations, for example. The other product that we have is our QKD system, QKey, that is based, that is a stable and robust QKD platform that works both for fiber and free space links. It's based on a three-state 1 decoy BB84 protocol that has been proven to be secure against the most general type of attacks. So it's, let's say, a well-known and mature protocol. It's polarization based, and we use a special type of encoder that we developed that is called Cognac, that is very stable. As I was saying, it integrates the quantum random number generator inside, and it's compatible with the HC04, 014, SKIP, and other type of, let's say, proprietary type of communication protocol. And it's a 2U, compact 2U system. These are the performances. We have we can have around 2.2 kilobits per second at 13 dB of losses. That's more or less the typical value. And we can go up to 20 dB with our standard version and 23 dB with the premium version. And also we tested the system with SNSPD. We actually have a partnership with Single Quantum to interface our commercial system with their commercial SNSPD. We can go more around 36 dB of losses in that case. So these are actually some of the key features of our system that I wanted to describe a bit, that might be a little bit different from also some other vendors. The first one is, let's say, our polarization encoder. As I was saying, we use polarization and as the way to encode information in our qubit. And to do that, to generate these polarization qubits, we developed this Cognac polarization encoder. It's a patented solution that, by using a Sagnac interferometer, offers a very long-term stability and also very high stability with respect to thermal and mechanical fluctuation, and at the same time also an extremely low quantum bit error rate. Here you see some measurement, and as you can see, we can go down below the 0.05% of quantum bit error rate. So very stable and very low error encoder. The other, let's say, key feature, a particular feature of our system is that we have a protocol, the qubit for sync protocol, that we use to synchronize, that only uses the qubits themselves. This means that we don't have any additional laser on detectors for the synchronization, but most importantly, we don't have any additional service fibers. So we just need one single simplex fiber to run our protocol. And in general, this can be very useful and crucial in scenarios, for example, where there are not so many fibers available. And so in this way, you can save up, let's say, resources, or if you don't have, you can still implement the QKD protocol. The other, let's say, peculiar feature is our quantum random number to qubit protocol. And this means that, as I was saying, each QKD transmitter contains a quantum random number generator inside, but also the quantum random number generator streams all the random numbers directly to the QKD transmitters, and all the choices that are done by the QKD transmitters actually are coming from a fresh random number that is somehow generated by the quantum random number generator. This is in contrast with other approaches where, for example, the quantum random number generator is used as a seed, and then a pseudo random number generator expands this randomness. We don't have this type of pseudo random number generators involved because, and we have this fresh generation of quantum random numbers because we believe that is the only way to achieve the highest level of security. And regarding the polarization encoding, this also, let's say, key feature. This choice was done mainly because in this way we can cover many different type of channels, such as fiber and free space, or also satellites, with the same type of encoders and devices. And also because this allows us to have, as you can see, as you have seen, a low quantum bit error rate. The other thing is also means that we don't need to match the transmitter and the receiver when at the factory. For example, this is instead something that sometimes happens with interferometric devices, time being or phase encoded. Instead, here we don't need this matching because we just need to align the polarization reference frames. We are compatible with point-to-point, but also star and ring topologies. We have a key manager system that is integrated in the devices and is compatible with the interoperable QKD operation. We are also compatible with the ETSI-04, the ETSI-014, the SKIP Cisco protocol. Others are available also on request. And we have tested our system that is compatible, and we tested it with encryptors from different vendors, such as ADVA, Rodenschwarz, Cisco, Thales, and we're always open to new partners. The last point that I want to stress is this point of interoperability and wavelength diversity. So our system, they work both in the O and in the C band. In the C band, we are inside one channel of the DWDM grid that is selectable by the user when they order the system. But the other important thing is that, as I was saying, these Alice and Bob don't need to be optically matched together, and they can work in an interoperable way. And also, since Bob is a broadband, we can work with the transmitter at different wavelengths. So, for example, you can have hélices, different hélices at different wavelengths transmitting to the same Bob receiver. And this is, at least from the customers, they told us that is really useful for complex and reconfigurable network topologies. Another point that, so now I want to show you a bit some results that we have. So, for example, an important aspect in the QKD system is actually from the point of view of the end user, is their stability. And this, for example, is a system that we've installed in a client facility. This is used in production over a dark fiber to secure a critical infrastructure in Italy, and works with the layer 2 encryptors from ADPA. And this system has been running for 7 months now. And as you can see, the system has an excellent stability over time. And also, if you can see the quantum bit error rate, it's around 0.58% over 2 weeks. in this time. So the system are stable. The other crucial point, we understand that it's important to show that the system can work together with the classical communication. This is one of the challenges in implementing the networks. So needs to work in coexistence with the classical communication, but also we need to check and develop a system that can work on different type of channels, such as fiber, free space, and satellites. So in Padova, for example, we're building a quantum network that is composed on different nodes. The blue ones are fibers, and the red ones are free space. We're deploying our system there to check and to test their operation in different conditions. And so we tested the coexistence, for example, between the VU6, that is our internet service provider at the university, and the calculus center of the university. We multiplexed quantum and classical communication over the same fiber with the quantum in the C-band, and the classical was around 1490. And you can see that also here we had very stable operation, still a pretty high quantum bit error rate, even though we had the multiplexing. Also, through the So also with the university, through the university, we've been working with the GAR consortium to develop and test again this coexistence. And we tested both the coexistence of QKD in the C-band and classical communication in the O-band, and also the vice versa. So with our system in the O-band and the classical communication in the C-band, we were still able to operate and get quantum keys also in these multiplexing scenarios. We also developed portable optical systems, so to implement free space communication that we tested together in this OpenQKD, let's say, use case with the team at Telecom Italia, where we multiplexed two different transmitters, one in fiber and one in free space, to the same receiver location, and we were time multiplexing them. And as you can see, we had a pretty stable operation over time. And also we had this intermodal use case with AAT in Vienna, where we had one portion of the link was in free space, one portion of the link was in fiber. And basically, we showed that the two links were compatible to each other, they could work together. And these are our system installed in the Vienna RACs. And the last one now is another let's say use case for OpenQKD that we developed between Matera and Oberpfaffenhofen at DLR in Munich, where we were securing the last mile connection with our system, and we also encrypted and relayed the keys with encryptors with a layer 2 over layer 3 encryption.
Okay, thank you very much.
And that's it.
Okay. Okay, thank you very much. Sorry we ran out of time. And I see there's a question in the chat. If there are other questions in the chat, please go there. Thank you again. Let's now go to the final presentation, which is last but not least, by Hans Brunner for Huawei.
Yes, well, starting my presentation now.
We can see it, but it's not presentation mode yet.
No.
Now it looks good.
Okay.
Please go ahead.
Well, thank you very much for inviting us. And sorry, Mario, not entanglement. We are also focusing on continuous variable QKD. The first thing I want to introduce is Huawei. I assume everybody has heard of Huawei before, but maybe you haven't heard that Huawei invests a lot in research and development. more than half of the employees actually work in R&D. And yes, also Huawei not only invests a lot in R&D, but it also invests a lot in Europe. There are thousands of research engineers here on 27 different sites. I'm based in Munich, where the quantum key distribution research happens. We started 8 years ago, and well, we have state-of-the-art CVQKD prototypes, not products, with lots of system-level field trials, mostly in Madrid, and yes, a lot of innovation there. I always like to use these talks to motivate again what we are doing here. I guess you all know Moscow's inequality, but I see a tiny issue with this. So Moscow's inequality says if you want to have your data secure for the duration D, and it takes you time T to transition to quantum security, you should start, well, actually in the past already now. But when you look at this, usually people think a cryptographically relevant quantum computer is the universal quantum computer. And I believe this is a bit tricky, because a device which might, let's take RSA as an example, a device, or people then say there might be an issue in 10 years from now. But the device which, for example, breaks RSA does not necessarily need to be universal gated quantum computer. It can be a very dedicated device, so it's a very different type of research actually. And while QKD and encryption in general are more now in the public domain, trying to focus on breaking it is in the military domain. So this research is very different and also more hidden in a sense. People definitely publish less about it. Also, research in Germany on this topic might even be against the law. So you will not hear a lot about it. And the third point is, if you're able to actually break it, this is an enormous advantage military, politically, and also economically. You'd never tell anyone. If someone knows that you can break it, the value of it drops significantly. So with this maybe a bit difficult point I'm trying to put forward here is I want to say maybe there is already something 10 years ago which was able to break it, and we really should start moving forward. What we have built are continuous variable quantum key distribution prototypes. We've tried to move most of the complexity from the optical domain to the digital domain, make the systems as simple as possible from our point of view. This makes sense because on the one hand, it's more flexible. You can more easily adapt new protocols. And on the other hand, the analog parts come with non-linearities or some behavior which you cannot predict perfectly, and also change their behavior over time, over temperature. And the more you move to the digital domain, the more you can control it. The same code will behave the same way also in the future. Also, we chose CV over DV. From practicality point of view, it can be built from off-the-shelf telecom components. You can see on the top right the logical block diagram of what's happening in our box, and it's just you modulate a laser, you attenuate it down, observe most of the power to be on the safe side, and then you send it over the fiber and have a coherent detection at the receiver. And when you look at the pictures below, which is the inside of our boxes, we are quite transparent here. It's really the same. There is this laser, you modulate it, attenuate it down, and then you go on the line. And at the receiver, it's just a coherent detection. So from my point of view, I mean, I've heard a lot about photonic integration, and photonic integration is a nice buzzword and people go for it. For CV, I don't believe that it makes, it's in the close future, it's more about improving the processing. Most of the issues of CV are not in the optics, it's the processing afterwards. In the left lower part, you can see our reach. We can support up to 21 dB of loss, which is outstanding for CV QKD. For most distances, we support a key rate of roughly 10 kilobit per second. And the red dots here are actual measurements from the devices. We are not just optical setups in the lab. These are on all layers implemented. Only the key management we have not implemented ourselves because we focus on the optics and the signal processing. We have installed a large test bed in Madrid, where we have brought 5 transmitters and 5 receivers in 7 different locations and connected them through in an optically switched setup. Could maybe take such a switch and with the 2 OEDMs to the right and left, look at it like a reconfigurable optical airdrop multiplexer. So for example, the signal which originates the transmitter in Quevedo could be sent either to Norte or to Quixote, and it can also be forwarded to the other nodes. And our senders and receivers can also be tuned to different to any wavelengths in the C-band. So here we implemented it on channel 37 and channel 38. To show this wavelengths configurability, to also show the any-to-any connection. So with the 5 transmitters and 5 receivers, we could, and the 2 different wavelengths, we could actually build 35 different links in this network, loop-free links. It was integrated with the key managers developed by the Polytechnical University of Madrid and also encryptors from Roland Schwarz. Also, we have tested what we call zero-touch integration. So if you already have a setup, like in the Quixote link, where we have 1 pair of fibers, and someone already has installed OTN equipment with a multiplexer, maybe there's an 8-channel multiplexer and only 4 of the ports are used so far, our QKD solution can simply be plugged to one of the 3 ports and it will work. So we could prove that it works. So we not only would need only a single fiber, we actually only need a single wavelength or single channel of a dense wavelength division multiplex setup if there are not too many other channels, and also there cannot be any amplifier. But apart from these restrictions, it can simply be plugged in and be used. So for the switching, just to emphasize that this really happened, here's the same picture as before, but drawing it less complex, still complex. The orange boxes are the senders, the green boxes are the receivers. And depending on how we configure the switch, we can realize different configurations in the network. And so, for example, in the configuration to the top right, the switches were configured such that Concepcion would send to Quevedo, Quevedo would send to Norte, Norte to Quintin, and so on, and also on different wavelengths. So on the fiber pair between Quevedo and Norte, there were actually 4 different QKD signals from our devices producing key at the same time. And on the top bottom right, there is a different configuration. This just to show that it really happened. These are the boxes we built and brought to Madrid. The QKD devices are the 2U height units up there, and they always come with a server. The rest is OTN equipment. So I believe we have thoroughly investigated and very robust QKD implementation. It's software defined for maximum flexibility and also central configuration. It's a low-cost implementation, clear road for full integration and high volume. Reach and key rate are optimal for the metro environment. This is also something I want to emphasize. CVQKD is very optimal for the metro environment. It has a very high tolerance, roughly 10 times more co-propagation than DV. there was this possibility of zero-touch integration, which can be useful for universities which connect different data centers, for example. And we have this field deployment where we tested all this also with the any-to-any connectivity. Okay, thank you very much.
Thank you very much. We do have time for questions. The testbed that you showed with the mini alien QKD boxes in Madrid, yeah. This was all different vendors than that you were working with, right? Oh, alien.
Well, the Madrid testbed is larger than just what we brought, and there were also QKD devices from Toshiba and ID Quantique.
Okay, very interesting. And how I mean, what distances did this encompass?
Well, it's not shown here. It covers the whole metropolitan area of Madrid. The actual distances are not so far. It's usually below 25 kilometers per link. But the actual losses per link, especially including all the OTN equipment, are usually pretty high. I don't know by heart, but I think like a link between Quiron and Quixote is already 15 dB. Also, it is maybe, I don't know, 20 kilometers. And also very short distances of 2 or 3 kilometers might be already in the order of 8 to 10 dB of loss, because it's old fiber, old patch panels, and
yeah, real life situations.
Real life situation, exactly.
Yeah. Okay, any other question? It does not seem to be. Oh yes, Manfred Nihus, please go ahead.
Yes, just a question regarding the photonic integration. You said it's not very, it's not maybe not the way to go, but this would also come with benefits in terms of form factor, maybe in terms of price. Could you comment on that, please?
Well, okay, maybe this was a bit of a bashing of photonic integration, which I did not intend. Yes, photonic integration definitely makes sense if you want to go for large scale, and it might also make sense for CVQKD already now for stability reasons. From the form factor point of view, in my opinion, the biggest challenge is the computational complexity CVQKD brings. In contrast to DV, which is, from my opinion, very analog, and the processing afterwards is rather simple. And CV, it's the other way around, where the optics are rather simple, but then you need a lot of processing afterwards, which takes a lot of computational power. And integrating this computational power, of course, it will reduce over time, but at the moment, it's, in my opinion, a way bigger challenge than the photonic integration. For example, in our prototypes, more than half the costs are for computation, and only maybe 20% are for the optics. So if you claim that you reduce the price a lot by photonic integration, in our prototypes you maybe reduce the small part of the optics by a factor, but the computation is, from our point of view, the bigger challenge.
Okay, thank you very much.
Okay, so thank you again. This brings us to the end of our 2 sessions. I want to thank all the speakers again for presenting a nice variety of solutions in the quantum field. And I will make all the presentations available on the agenda. Some are already available. For those of you who haven't submitted it yet, please do so. And also the recording will be available as soon as we have it. I will post it on the event site and you can get it from there. So thank you also for all the participants that joined and made this a very interesting session. Thank you and have a nice afternoon.